the error analysis here. So the question comes up, how close can we get using, oh, let me back up a step there. So we have a need for finding numerical approximations to integrals that we can't find a closed form solution to. So things like e to the x squared or sine of x squared don't have closed form solutions. That is, you cannot write, even though Macy is going to devote her life to trying to find a function whose derivative is e to the x squared, I think it will be a squandered life. It doesn't exist. I think you should set your sights on something more impactful. So the question of, it's still a continuous function, and so we still would like to be able to integrate it in the sense of, can we find the area between the curve and the x-axis between whatever 2 points we're interested in. So to do that, we need to approximate it some way numerically. So rectangles are nice to understand conceptually, but they're not very efficient. You know, to try to approximate an area under a curve using rectangles is just inherently, you know, trying to fit a square peg into a round hole. It doesn't go very well. So a trapezoid is an improvement on that. And what we talked about on the video from Friday, using parabolas, is an even better way of approximating that. So what Simpson's rule is doing, just to recall, is if you have some curve and we want to approximate this area between the curve and the x-axis from A to B, that is, we're trying to approximate that definite integral, we said if we subdivide this into an even number of subintervals, then evenly spaced, so an even number of subintervals that are uniform in width, then what we can essentially do is find a parabola between successive points. So the idea is between those 3 points we can find a parabola. Between these 3 points we can find a different parabola, and so on. And we can then find the area between that parabola and the x-axis, and then the area between that area and the x-axis, and so on. And that's a much better approximation even than the trapezoidal rule, which is a better approximation than rectangles. So for this to really be useful, we need it to be prescriptive. So if we have some integral that we can't find a closed form integral of, and we need to approximate it to some particular level of accuracy, say 1/100,000th, then we need to know how many trapezoids is that going to take to get within our error margin, within an error that we can live with. You know, we're trying to send somebody to the moon or to Mars. We have to have a certain level of accuracy or we're going to miss and send them on the last trip of their life. And so we would like to get there and get back, so we would like to be able to hit that target. And so we need a certain level of accuracy. So then if it's prescriptive, we need to be within this certain level of accuracy. Then how many trapezoids or how many subintervals, if we're going to use Simpson's rule, do we need? And so that's where this error analysis comes in. And so these formulas have been developed with not a ton more math than what you know now, to be honest with you. And so we are going to try to develop them, but we have the error formula for our trapezoid. So we'll say the absolute value of the error. So this means the difference between our approximation using a trapezoidal rule and the actual true area between the curve and the x-axis, it turns out is less than or equal to b minus a over 3, b minus a to the third, all over 12n squared, times, and this is the part that maybe takes a little understanding, the maximum the maximum of the absolute value of the second derivative of x, where x is between a and b. And so that's the error. And I'm going to put up here also the error for Simpson's rule. And then we'll kind of compare and contrast them. And then we'll actually use these on a particular function to estimate this error. So Simpson's rule is b minus a to the fifth over 180 n to the fourth times the maximum of the absolute value of the fourth derivative of x on that interval from a to b. So some of these things I think make sense, some are a little surprising perhaps, but the idea is that the error, the error will be bigger the larger the interval from A to B is. If we're taking a short interval, then this error is going to be smaller. If it gets big, then when you take that length of that interval to the third power or to the fifth power, that error is going to get big. And so it's going to be more difficult. Now, the error gets smaller, the more subintervals we choose. So here n is the number of trapezoids. So the more trapezoids we make, the shorter the subintervals, the better the accuracy. So n goes up in the denominator, the error goes down. And in a bigger way with Simpson's rule, because now it's to the fourth power. Now, somehow it also depends on the curviness of the function, right? Especially that's clear with trapezoidal rule. Since with a trapezoidal rule, we're trying to approximate that area under the curve using straight line segments for our trapezoid. The flatter it is, or the more linear it is, the better our approximations are going to be for each individual trapezoid. The wilder it bends, if our function's, doing something like this, now trying to approximate those with trapezoids gets less accurate. And so there's a bound in here that has to do with the largest the second derivative can be on the interval from A to B. So a bigger second derivative is going to mean a more curvy function, and the less accurate our trapezoids are going to be. And you can see that a second derivative of a linear function, y equals mx plus b, the second derivative there, well, the first derivative of mx plus b is m. The second derivative is the derivative of the slope is 0. So the largest the second derivative can be for a straight line is 0, which means that a trapezoid is going to approximate a line with 100% accuracy, which makes sense, right? And if it gets more than a linear, once you get to a quadratic or cubic or who knows, sine curve or exponential, whatever it is, then the accuracy is going to get worse. What's kind of surprising, I find anyway, is that you're approximating with Simpson's rule using parabolas. So it would be reasonable to think that if you were going to approximate a function that was quadratic, that is itself a parabola, using parabolas to approximate a parabola should be spot on, and it is, because the first derivative, is going to be 2ax plus b, the second derivative is going to be 2, and the third derivative is going to be 0. What is surprising is that it goes all the way to the largest that the fourth derivative can be, which means a cubic will be approximated with no error exactly with Simpson's rule that's using parabolas along the way, which is kind of surprising. So somehow you get an extra kind of boost in accuracy out of Simpson's rule.
So if you were using Simpson's rule to approximate a line,
you would still get 100% accuracy because the fourth derivative of a line would also be 0.
how would that work, like visually?
Yeah, visually it's hard to see. I would agree. I'm not sure quite how that would look. But at least in our theory here,
Okay.
you get 100% accuracy. Okay, so that's kind of the idea, kind of looking at these formulas and seeing what they're saying. So let's see if we can do it in practice. So we're going to say, let's find n. I don't have enough room on one little board here. But we'll see what we can do. So we're going to find n, the number of subintervals. So the error in approximating the integral from 1 to 3 of 1 over x dx is less than, and we'll say decimal point 1, 2, 3, 4 zeros and a 1. 1, 2, 3, 4 zeros, 1. First using trapezoidal rule and then using Simpson's rule. So this is tenths, hundreds, thousands, 10 thousands, 1/100,000. So we want our accuracy to be within 1/100,000th of the actual integral. Does that make sense? And so what we want to do is use our error formula as a prescription to say, okay, if you're going to do trapezoidal rule, this is how many trapezoids you need to do. This is the minimum number of trapezoids you need to get within 1/100,000th. Using more than that will just get you better accuracy. But if you need to be within 1/100,000th of determining your trajectory on that rocket launch to send Cameron to the moon, this is how many we're going to need to use, how many trapezoids. You don't want to choose less than that. You don't want to run the risk of saying goodbye to Cameron as he flies off to the moon. Okay? So here's what we got. We want our error to be less than 1/100,000. So you want this to be less than 1/100,000. Okay? So what's the B minus A? Oh, I want to use yellow for this one. Hold on. Let me pick a different color. We got pink, yellow, and purple. Okay, you want the purple here. So we're going to less than 0.00001. So what is our B minus A? 2. So that's 2 to the 5th over 12.
Wait,
Yen.
are you starting with, is this the trapezoidal rule?
This is a trapezoidal rule.
Yep. Shouldn't it be 2 to the 3rd?
2 to the 3rd. That's your way. So our error is going to be 2 to the 3rd, 12n squared. Struggling here, right off the gate. So we want this. Now we need the maximum of the second derivative to be less than, and we're going to call this 1 over 100,000. Okay, so let's talk about this second derivative. Okay? So our function is f of x equals 1 over x, which for derivative purposes we're going to think of as x to the negative 1. So f prime of x is going to be negative x to the negative 2. And f double prime of x is going to be 2x to the negative 3, which we're going to think of as being 2 over x to the 3rd. Now here's the reasoning that goes into this. We okay so far? So we want the largest that the absolute value of this derivative can be between 1 and 3. Now our x is in the denominator. So we're looking at these numbers between 1 and 3, and we want to know what's the largest that 2 over x to the 3rd could be. So a fraction is the biggest when its denominator is the smallest. So on the interval from 1 to 3, that's going to be when x is 1. Follow that reasoning? Which means the largest that our second derivative can be is 2. And so that is what goes here. Okay? Now the rest of it's just a big algebra problem we're solving for n. And we'll need our calculator at some point along the way here. So let's see, we can cancel this 2 with that 12, making it 6. We can cancel one of those 2's with that 6, making it 3, we don't have to do that. We got 4 over 3n squared. That's less than 1 over 100,000. Okay, so far? So I'm gonna,
Where did the 4 come from?
I just canceled that 2 to the third
Oh,
with
yeah,
one of
okay.
the 2 in there. Is that okay? Gotcha. So the 2 to the third, I canceled one of the 2's with the 2 in the 6. After I canceled
Oh,
one of the 2's in the
okay.
12 with the 2 from the largest, the second derivative could be. We okay to that? So we all right with 4 over 3n squared so far?
Yes.
Okay, you nod your heads. I'm going to take the reciprocal of both sides. And when you take the reciprocal of both sides of a fraction, so if we had, 2 is less than, let me say 1 is less than 2. If I take the reciprocal of both sides, then we have to change the direction of the inequality for it to still be true. So we're going to, when we take the reciprocal of both sides, that's going to make this be 3n squared over 4, but it's going to turn it into a greater than 100,000 over 1. Which makes better sense, because we want to know what's the minimum number of n we need. So we can multiply by 4, divide by 3, and take the square root of that on your calculator. So n is going to be greater than 400,000 over 3, taking that square root. And go ahead and give me it to the nearest tenth, because then we'll talk about the fact that n has to be an integer, because it's going to be a number of trapezoids.
About 365.1.
365.1. Now remember, we want at least accuracy to 1/100,000th. We don't want to risk missing the moon as we launch our astronaut. So what's the minimum number of trapezoids we're going to need? 366. So that's the minimum number of trapezoids we're going to need to approximate that and get within 1/100,000th of accuracy. Okay? Now let's do it with simple question.
Oh, no, I answered my own question. Sorry, I just forgot to put the range.
Okay. So now we're going to do it with Simpson's rule, and we'll see how much more efficient using these little parabolas is. So our b minus a is still going to be 2. So that's 2 to the 5th over 180 n to the 4th. Now, we need the largest that the 4th derivative can be. So we have the second derivative here. And I'm running out of room, so I'm going to steal some from up here. So our third derivative is going to be negative 6x to the negative 4. That okay? And then our fourth derivative is going to be 24x to the negative 5, which is 24 over x to the 5th. So again, we're saying what's the largest that can be on our interval from 1 to 3. So again, we've got that x to the 5th in the denominator, and the largest a fraction can be is when its denominator is the smallest. So between 1 and 3, the smallest it can be is 1, which makes the largest that our fourth derivative can be 24. Is that okay? Well, I don't know if I even want to try canceling here. I guess we could say 6 goes into here 30 times, into there 4 times. 2 goes into there 15 times, 2 more. Go about at the end of the road. 32 times 2 is 64 over 15 n to the 4th. And we want this to be less than or equal to 1 over 100,000 at this point. I guess we'll go strictly less than. Is that okay? Our same story, we're going to take the reciprocal of both sides. So that's 15 n to the 4th over 64 is now greater than 100,000. Is that okay? You right with that? So then I'm gonna multiply by the reciprocal. So we're gonna take the 64 times the 100,000 divided by the 15. And then we're gonna take that to the 1/4 power. And you can tell me that to, say, the nearest tenth before we decide how many that's telling us. Let's,
Thank you. I got 25.6, but I could use
everybody else getting that as well? I think that's pretty close. So that means we need how many subdivisions? Compared to 366. Pretty remarkable.
Do we need to memorize these equations?
No. No, I'll give them to you if I want you to use them. So it's kind of interesting. There's a whole part of math that does a lot of this kind of stuff where these formulas are developed, just numerical analysis, because there's great need and use for this. And the reality is a lot of integrals can't be done. And so if you can harness the computer, program it, Simpson's rule is very programmable, so and a computer can crunch those numbers. It doesn't mind doing 366 iterations, this would be a walk in the park. So you can get great accuracy, even, when you need a lot of subintervals. If you can, access that kind of computing power. So this is useful stuff. There's a lot of this done. And so it's kind of a glimpse into that world. Questions on that? Anything else? Well, you can see that the review has some good weight to it. So you can have 12 minutes to continue working on that.